or the synonym for to that is the range of a linear map. And surprise, surprise, this one will cover the second half of my subspaces. So you see my subspaces from before, I split them in two classes. The first class I now neatly covered by null spaces of linear maps. The second one will be covered by this range or image type. Range or image of linear maps. Look at this. So here's my typical setting of a linear map. Here's a quadruple for the domain. Here's a quadruple for the codomain. Here's my two vector spaces. T is a linear map. Look how I'm going to define the image of a linear map. Image of a linear map. These are all the vectors from my codomain, which can be produced as the result of my action of T. So you see what it says here? It's all vectors from the codomain, from W, such that these vectors are result of action of T on some vector from the domain. Or you can write it shorter. It's all possible T of X where X runs across V. It's two different ways to write this. Essentially, it's identical way. In line what I just presented for the null spaces, I claim, and that will be another lemma for today, that the image of the linear map is a subspace. Okay, so again, when you argue something is subspace, the first approach maybe will be by subspace theorem, and my proof here will go by subspace theorem. I need to test three criteria of a subspace theorem. Here's my careful test. First, I'll make this observation. We all know that the 0 is taken to 0 by linear map, which means that you can produce a 0 vector here by taking here a 0 vector. And that is enough evidence that 0 is a part of the image of a linear map. Second part is this. I fix two vectors, and because now I can't use x and y, I will call them y1 and y2 from the image. I interpret what that means. The interpretation of being in the image, it means that the vector may be reproduced as a result of action of T. So here's my interpretation. There are two vectors, x1 and x2, in the domain, such that y1 is a result of T action on x1, and y2 is a result of T action on x2 together. From this, it's not far to see that if I take the sum of vectors y1 and y2, by subbing in these two expressions from the right-hand side, is my substitution. If I use the linearity of the T map, I can convert it into something like this, and that is enough evidence that the sum of y1 and y2 is the result of action of T on some vector from the domain. And that's why y1 plus y2 is a part of the image. And that's enough evidence, and that's the second criterion, positively tested. Now the third criterion, the same type of argument. I start with the element y from the image. I interpret what that means. It means that I have a vector x in the domain such that this y is given as a result of T acting on x. Now, if I'd like to see y, scaled vector y is a part of the image, I make this observation. First, I replace my y with a T of x, is a replacement. Then again, I use the linearity of my linear map, is the usage of linearity. And then here's my argument now. My new vector, lambda times y, is the result of action t on some vector from the domain. That's why the vector is in the image. And that's the finish of the proof.